Well, we made it to Chapter 9 of Surviving Statistics. In this chapter, we're going to talk about confidence intervals and point estimates. A point estimate is one specific value. So in the last chapter, we saw that we can indeed estimate population values based on statistics that we compute from samples. For example, to estimate the mean GPA of a population of 10 students, we did take a sample of 2 students and we computed the mean. That sample mean is our best estimate of the population mean. But we saw, especially when we created a sampling distribution of the sample means, that some of those means are far off from the actual population mean, and some of them are a little bit closer. That is due to sampling error. Well, one way to make up for that is to use an interval or range of values rather than just a point value or a point estimate. A point estimate is one specific value, as I mentioned, such as a sample mean. Well, we know that that's not necessarily going to represent exactly the true population mean. And so a confidence interval allows us to compute a range of values, a value higher than the sample mean that we computed and also lower than in the range within those two. And we will then specify certain levels of confidence. Within statistics, typically we're going to be using anything from a 90 to a 99% level of confidence. So for example, if I'm using a 95% confidence level, the range that I compute, higher and lower than the sample mean, allows me to be 95% confident that the true population parameter, the true population mean, will fall within that range. Now I do that by computing what's called a margin of error. The margin of error will be based on how accurate or confident I want to be, and once I compute that margin of error, I will then add that to the sample mean and then subtract it from the sample mean, giving me a range of values based on the margin of error, and we'll show you how to compute that margin of error next. All right, let's go ahead and use our 10 student GPAs as an example of how to create a margin of error. So again, the margin of error is going to be added to and subtracted from the sample mean that we compute. So let's assume in this case that we select a random sample of 2 students and we end up with Ahmad and Kathy, and the sample mean is 3.0. Well, we know right off the bat just by looking here that that is not exactly correct, but we want to be, let's assume we did not know what the population mean was, we want to be 95% confident that we're estimating the true population mean. So we're going to choose a 95% confidence interval. Then we're going to compute that range of values and add it to 3.0 and subtract it from 3.0, and the range that we end up computing will let us be 95% confident that the actual range, or the actual mean, in this case lies within that range. So let's see how that works. We actually compute the margin of error 2 different ways based on whether or not we know or have available to us the population standard deviation. In this case, we're going to assume we do, and so we're going to compute the formula the first time, assuming that we know the population standard deviation. So in this case, we have the margin of error formula is the z-score associated with the level of confidence. We want to use 95%. We'll come up with the z-score here in just a second. Then we are multiplying that by the population standard deviation divided by the square root of n, the number in the sample. So we've already computed this population standard deviation of that class. We're assuming it's a population of 0.5643. The sample size is 2, so we have everything we need now except for the z-score to use for a 95% confidence level. Because we're dealing with a range that is going to be lower and higher, we're looking on both sides of the mean that we computed in this case, this is going to be a two-tailed test. So for a 95% confidence level, we're going to have 2.5% at each tail. And so we're going to be looking for the z-score that equates to an area under the curve of 0.4750. Okay, this time we want to find a z-score associated with a specific area. In previous chapters, we have found the area based on the z-score. So we're looking for 0.4750. We use the normal distribution table. We find it, of course, in this case it happens to be highlighted for us. We see then that it is 1.96. So the z-score that we're going to be using is 1.96. Well, now that we've located the z-score associated with a 95% confidence level, we can compute the margin of error. So we take the z-score that we found, 1.96, we multiply that by the population standard deviation divided by the square root of n, and we end up with a margin of error of 0.782. Now we're going to subtract that from and add that to the mean that we computed for those two students of 3.0, and then we end up then with a range of 2.218 2 on the high end, 3.782. Now we can be 95% confident that the true population mean is between those two values. Well, the actual population mean was 3.11, and so that definitely falls within that range that we computed. Our previous formula that we just used for computing the margin of error required that we know the population standard deviation. Now, if we're conducting research on our own, especially original research, it's very unlikely that we're going to have those parameters, such as the population mean and the standard deviation of the population. Often that's what we're trying to estimate by our research. So this might seem to be a problem, but it simply means that we're not able to use z-scores to compute our margin of error. Fortunately for us, though, statisticians have solved the problem by creating another distribution called the t-distribution. All right, the t-distribution is very similar to a regular normal curve. It's a little flatter, and there's a little bit more information on the edges, a little bit more dispersed around the mean. Now, we're going to be using a t-score in this case because we do not have the population standard deviation to compute the margin of error. In real life, in statistics, we often use the t-score with smaller sample sizes, usually of less than 30. Now, when we're working with the t-distribution, we're going to be working with something else as well, and that is the degrees of freedom. Now, the degrees of freedom is going to be computed by n, the sample size, minus 1. So the sample size is an integral part of the t-score values that you're going to find on the t-score distribution table. So let's run through an example of using the t-distribution. So in this case, let's assume that the 10 students that we have, the GPAs from the stats class, are not a population anymore. Now they're a sample. They represent every statistics student in the college. What we want to do, just as we did with the z-score, is we want to create a 95% confidence interval for the means of all the students in the college. And we'll use a sample mean to do that. We're going to use, in this case, the sample mean that we compute of these 10 students, which is 3.11. We're also going to use the sample standard deviation, which we've computed as 0.5948. All right, so here's the formula to compute the margin of error when we do not know the population standard deviation. We once again use the standard deviation. In this case, though, it's the sample standard deviation. We use the square root of the sample size, and instead of multiplying that by the z-score, we multiply it by a t-score. Now the t-score, as I mentioned, is going to use degrees of freedom, which is n minus 1. So our degrees of freedom are going to be 9. Our confidence interval is also going to include a value larger than and smaller than the sample mean that we've computed, so it's going to be a two-tail test, just like the z-score was. Well, let's go ahead and see how to look up a t-score in a distribution table. All right, so here we see an example, an excerpt from a t-distribution table. And up at the very top, you see one tail and two tail. Well, this is a two-tail test with 95% confidence, so that means that we're looking for 5% in two tails. Or if it were a one-tail test, we'll end up with the same value, 2.5% in one tail. But in this case, it is two-tail test, 5% total, 2.5% in each tail. So the degrees of freedom are extremely important here. So we scroll down the far left column looking for degrees of freedom of 9. We then scroll over to the 95% confidence interval with a two-tailed test, and we come up with a value of 2.262. So that's our t-score. That's a little higher than we came up with the z-score of 1.96. So t-scores are typically larger because, as I mentioned earlier, the distribution is a little flatter, and quite honestly, it's not as accurate because we're using a sample standard deviation rather than the population standard deviation, so we're giving us a little bit more leeway. The range will be larger for a 95% confidence interval using a t-score. All right, let me remind you again what we were doing. We had our 10 students in our statistics class, and we took their sample mean, all 10 of them, came up with 3.11. We're trying to estimate the GPA of all of the statistics students in the class using that sample mean of 3.11. So computing now the margin of error, we end up then using the t-score, the sample standard deviation, and the square root of the sample size, a margin of error of 0.903. We then add that to and subtract it from 3.11, and we get a confidence interval of 2.207 and 4.013. So we can be 95% confident that the population mean will fall within that range. Well, obviously we know, at least in college, we're not going to have a GPA above 4. So we're even a little higher than we need to be, but again, that's the range we've computed, and we can be, with 95% certainty, confident that the population mean falls within that range. So when it's time to compute a confidence interval and a margin of error, do we use Z or T? Well, it's very, very simple. If we know the population standard deviation, we use the Z distribution. If not, we use the T distribution. Now, I'd be remiss a little bit if I didn't mention sample size. We'll get into that a little bit later on in the textbook here, but when we're dealing with sample sizes of typically more than 30, we can even use the Z for samples, but let's not worry about that just now. Well, now let's go ahead and discuss confidence intervals for proportions. A proportion is a ratio or a fraction, or typically expressed as a percentage. So an example might be the ratio of students who failed a course over all the students who took the course, the proportion of products coming off an assembly line which failed the final inspection. Proportions rely on the nominal scale, and it's similar to the binomial probability in that we have only one or two possibilities, answers yes or no, pass or fail. So the formula to compute a sample proportion is the proportion would be x, which is the number or the attribute that answered yes or passed, divided by the sample size. So if we surveyed 100 people and 10 of them had failed the test, then in that case the proportion would be 1 over 10. So here's an example of computing a confidence interval for a proportion. So let's assume that we sampled 100 moviegoers and asked, did you like the last movie that you watched? 40 of those 100 answered yes. So our proportion would be 40 over 100, or 0.4. So what we'd like to do in this case is compute a 95% confidence interval for the sample proportion to see what proportion of the population of moviegoers would like the last movie that they've seen. So in this case, the formula is the confidence interval is plus or minus the z-score times the square root of the proportion times 1 minus the proportion divided by the sample size. We'll go through it with our moviegoers and see how it comes out. All right, one of the z-scores that we probably have already memorized right now is 1.96, and we should recall that 1.96 gives us a 95% confidence interval in a two-tailed test, which leaves 2.5% at each tail. So now that we have the z-score, and we use the z-score even though we don't have the population standard deviation because you don't have standard deviations with proportions. So we compute then the confidence interval, the margin of error being 0.096. So we add that to and subtract it from our 0.4 sample proportion, and we end up with a confidence interval of 0.304 to 4.496. So we can be 95% confident that the proportion of moviegoers who like the last movie they saw falls somewhere between 0.304 and 0.496. We are halfway through this textbook on the statistics course, and we've seen that the sample size does affect many different computations. So coming up with the right sample size is extremely important. And so how do we do that? Well, computing the correct sample size depends on three things. Number one, the allowable acceptable margin of error, the desired level of confidence, and, if you know it, the dispersion or the standard deviation of the population being studied. Well, as you might have guessed, there is a formula to determine the correct sample size. And here we see the formula. The sample size equates to a z-score that you're looking for, which is the confidence, the standard deviation, and we're also going to include the allowable margin of error. And we'll step through this in the next slide. All right, so let's assume that what we're setting out to do is survey the entire population of all the students in a particular college that are taking statistics. So these are our parameters. We want a 95% confidence level, and we're only willing to accept a very small zero point 0.1 or 10% margin of error. So we don't have the population standard deviation. So does that mean that in this case that we cannot compute a sample size and we should just give up? Well, fortunately, there's a way for us to be able to still compute the sample size with an unknown population standard deviation. And we're going to use an estimate of the population standard deviation to do that. So if we do not know the population standard deviation, it doesn't mean that we have to give up. There are some ways that we can estimate the population standard deviation to compute the sample size. One way is to use data from previous studies or to conduct our own pilot study and use the standard deviation that we compute as our estimate of the population standard deviation. We can also estimate the standard deviation from the population range if we know it. In this case, we actually do know the range of GPAs. They're going to run from 0 to 4. So if we know the range, we can then divide the range by either 4 or 6 to estimate the population standard deviation. So you're probably thinking to yourself, where do these numbers 4 or 6 come from? Somebody didn't just pull them out of a hat. Well, here's the way it works. Remember the empirical rule? The empirical rule tells us that all values, nearly all values, 99.7% of the values fall within plus or minus 3 standard deviations of the mean. Well, there's 6, 3 on each side. The empirical rule also tells us 94.7 falls within 2 plus or minus 2 standard deviations of the mean, and that equates to 4. All right, so reminding you of the parameters that we wanted to compute the sample size, we were looking for a maximum margin of error of 0.1, and we wanted a 95% confidence interval. So we've estimated the population standard deviation by taking the range of the GPA and dividing that by 6 because we want a very accurate estimate. So in that case, then our estimate of the population standard deviation is going to be 0.667. So now we then compute the correct sample size of 171. Well, again, we took the z-score of 1.96. That represents the 95% confidence level with 2.5% at each tail. Notice that the sample size that we've computed here of 171 is far larger than the 10 student sample size that we've been using. But our interval, our maximum interval for the margin of error is very small in this case, and that's why the sample size was computed so large in this case. All right, let's just review some of the concepts we talked about in Chapter 9. We talked about a point estimate, and a point estimate is the best estimate that we have of a population proportion based on a sample statistic. We talked about a confidence interval, and the confidence interval is a range of values of which we can be a certain percentage confident that the parameters or the population mean or standard deviation or proportion, whatever we're wanting to measure, will fall within. A confidence interval, remember, will be plus or minus the margin of error. We compute the margin of error using the formula of the z statistic that equates to the margin of confidence level that you're looking for with the population standard deviation divided by the square root of the sample size. If you do not know the population standard deviation, you use the t-distribution, which uses the sample distribution. The t-distribution, remember, uses degrees of freedom, which is n minus 1. And we also saw a formula for computing the sample size for a population mean, and we saw that there were ways to estimate this population standard deviation if we did not have it. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.